I don't have. So, but we'll look at the results. I'll definitely go through your books. Every year I get a good recommendation, and then some things that I'm like, yeah, maybe not. But I looked at your topics. A lot of them are ones that we're going to cover, and there's some things that I want to talk about with you guys. Let's look at the survey result at the end. I think the questions at the end are the most important part. This is both sections, okay, not just you guys. We're collated over about 50 students. Dogs and cats are basically on a tie. It actually, if I remember correctly, the last time I looked, dogs were winning. I think dogs are still winning if you look at the numbers. Yeah, dogs barely win. I think that's pretty typical. I'd be interested to see that statistic across the programs. I think STEM people are more cat friendly than other programs.
Yes.
Yeah. Okay. Yeah. That's yeah. This is a very cat friendly class. Well, we'll talk about killing cats in this class. So, sometimes we won't kill them though. Physical chemistry is kind of half and half. That's fine. Most of you suffered through PChem 1. Only a couple of you are in here for PChem 2, so you don't quite as bitter as you would be otherwise. But that's good. I'm happy that it's about half. That's what I want out of the class. I can't really ask for more. If it was all red, then I know I have no problem. You guys equally hate integration by parts as much as pink drink, which is interesting. Hated rivalries, just like PChem, half and half. But what I got from the response from the other class is that most people didn't know what it was, so they just like whatever. Vectors are positive, magnets are positive. I hope you've enjoyed the first module because it's all magnets and vectors. Taylor Swift and Mr. Beast are equally hated. That's changed. That's a big change. Taylor Swift was much more positive in previous years. Clearly, she's fallen off the map a little bit. We're all bad buddies now. And then you guys love soul food. Thank God. Even more than you love Albert Einstein, which is actually the same way I feel. I like soul food more than Albert Einstein. Non-complex numbers, it is kind of the result. Some of you probably find them to be an interesting concept, and other you are scared by them. I think that's both perfectly fine. New Jersey is also hated, which is a change. I don't think we have a lot of Jersey kids this year. And then geometry kind of half and half. I wish I had more geometry in this class, but there is geometry and quantum mechanics, but we're not going to really have a chance to appreciate that. So that's good. That kind of puts me where I know you guys are, and it's more or less what I expected. So I did not realize Taylor Swift was this disliked, though. So that's the news to me. Okay. What else? Anything else I want to say? No, I have an announcement. I'm going to send out a post on Canvas. I don't know if it's of interest to anyone, but the surf applications are out. If anyone wants to do a surf project with me, I'll send some information about it. You can contact me if you need something to do this summer. I'm here this summer. Usually I'm out of town most of June and July for conferences and science travel. It's when I can actually think for myself. I don't get a lot of time to think during the year. I'm not going to my conferences this year, so I need something to do in the summer. So if anyone's interested, a junior perhaps. I can't really take seniors since it's for undergrads. If you're a sophomore or a junior, I know we have a couple sophomores in here. Something to think about. I'll send some more information about the projects I'm working on. They'll be mostly remote. You don't have to be on campus for it. And I can get you basically the program. They're all mostly computational projects. If you're interested in learning how to work with scientific research grade supercomputers, doing calculations at large scale, learn a little bit about Linux and using a computer for scientific research, I'm the place to come to. So I'll send you some information if you're interested. Let's return to our discussion. Today we can finally, after a little more discussion of this free particle, the idea of having an atom just moving freely in a space. We're going to get pretty close to something that at the end of the class today that I call chemistry, right? We can start making predictions, chemical properties, just a little bit of information. And we'll immediately be able to apply this and have a really nice application, this free particle idea in just a minute. So we're talking again about a particle that we define in terms of position. All right, so we've got our sensors all over the floor, and we put an atom or an electron. It could be any object. Someone in the other class asked, is there a mass limit to the size of the object that can act like this? Because you can think, well, it might work for an atom but does it work for a human being? Right? I'll answer that question for you, right? In reality, all objects, massive or non-massive objects, follow these rules. We'll see why it doesn't necessarily apply to you and me. Why I can't think of us as waves. Why that's not really a useful concept for a baseball, for instance. We can actually come up with an idea of kind of get a sense of where the wave properties of material become important compared to like the particulate. Just thinking of it as a ball instead. And so we can look at that. We can look at those scales. We actually have all the information we need right here. We just need some numbers and think about things. What I want to get at though is that we looked at momentum and position for these objects, and then realized that we can think about the energy by squaring the momentum, dividing by the mass. And when we did that, with the equations for the operators, the measurements that we have, we get this interesting differential equation that says that if we take the second derivative of whatever the wave function is of the system, we get it back times the energy times some numbers. Right? So whatever this measures, if you take a second derivative of the wave function, and whatever that wave function is, it should come back unchanged. Which means this wave function can only be a function where the second derivative is the function. But that really limits our list of functions. We came up with two exponentials and trig functions, sines and cosines. Realized neither of them work. And then I showed you this solution that you guys would both have right. That we need to combine the idea of an exponential and a trig function. And the only way to do that is to include an I. Right? We showed through Euler's formula that if you have a complex exponential, that's just two trig functions with an I in them. So it's a complex number where the real component, the x component is called the real part, cosine, and the y part is a sine, which is the imaginary part. And that just traces out as a function of x, circle. So as x increases, and you're just moving clockwise around this circle in complex space. So what that means is that the system is evolving like a wave. A wave is just something that oscillates around a circle, has a phase that oscillates around a circle, and that's what this particle is. It's a wave that acts like a wave. The K has to do with how much energy you pump into the system, right? So K is kind of like the frequency of that wave, right? Kx. And so the idea is that as K increases, which means you increase the energy of the system, the frequency increases, right? So for every step of x, you're going around that circle faster and faster. Okay, so it's like a velocity, a circular velocity, which is just a frequency. It's an angular frequency. It's how fast you move around the circle. All right, so there's this, so you can think this system is moving in XY plane. The way to really think about it is that it's a wave that's oscillating back and forth. A better way, maybe a way to think about this, for instance, is to think about our particle as an object that has some position. If you think about it as something that has position, it's moving in some direction that's specified by k, the wave vector. Right, so k tells you in some sense what direction it's going, or x, kx. So it's moving in this x direction. I should write x, sorry. Not k. This is moving in the x direction. And the way that it actually looks like is the sine wave and a cosine wave. So you have a sine wave or a cosine wave along the real axis. So the wave the particle propagates through space like a cosine. All right, so there's that component, but that's the real component. And then there's a perpendicular component. Of course, it's perpendicular because the I means that the vector, if you have an imaginary vector pointing towards y, a real vector pointing towards x, they're perpendicular. So these are two perpendicular functions, meaning that the waves propagate 90 degrees to each other. So there's another wave, which is a sine wave of the same frequency that's propagating in the perpendicular direction. Right, and the idea is that so one wave is moving like this, the red one is moving longitudinally, as we call it, and the other one is moving XY, transverse, like this. Okay, so the wave is propagating along two fronts, a transverse and a longitudinal wave. And so it has two components. It's a two-component wave from our perspective. So we have the longitudinal component and the transverse component. All right, this could be an atom. This could be any object, right? Any object that's represented by this psi, free particle, has this wave-like structure as it propagates through space. This is not a crazy idea. It's a little crazy that an atom, something of mass, has this wave-like property, but this is exactly the way the light works. If I replace this with a massless particle, a photon, a light particle, it propagates through space with this vector k, the wave vector, and there are two components. There's a cosine component that follows longitudinally along the direction of the vector. And then there's a perpendicular transverse wave that propagates perpendicular to it. And we have names for these. Okay? You can think of it as longitudinal and transverse. One propagates xy, the other one propagates up down like this. But we have names for these. That's what Maxwell gives us. The longitudinal wave is the electric field. And the transverse wave, which I have in yellow, is the magnetic field. Okay, so light works exactly the same way. The only difference is that an atom doesn't move at the speed of light. It has a mass, so it has the velocity that follows the speed of light. And of course, photons only travel at the speed of light. But they have the same structure, wavelength. Right? They have a longitudinal and transverse. This doesn't mean that the transverse component of the atom is a magnetic field. We're not assuming anything about the electrical properties of this atom. You can just think of it as a dumb neutral ball, but it still has that same structure. Let's look at a couple of properties of this system, right? So one question we should ask is, what's the probability? So I put the atom in this room. What's the probability where do I find it in a room? How do I figure out where it might be? Right. And we know that from previous lecture that what we do is we square the wave function and integrate over it. We take a square. That's what we observe, the probability distribution, which is the square of the wave function. That's the Born probability rule. And to get the total probability, we integrate over the function. All right, so let's look at that a little bit, right? So the probability, the atom is in some region. All right, let's just say it's between 0 and x. All right, let's say 0 and z. I don't like z. x1. Okay, is going to be equal to the integral from 0 to x1 of the wave function squared dx. Okay, that was Born's probability. Right, I can certainly integrate over infinity if the box is infinite. Right, we can look at that in a second. Well, we'll just leave it simple finite bounds. All right, we know that the system, the electron is somewhere. Right, so if I integrate over the entire space, the probability has to be equal to 1. Right, so if this is the whole space, I know the answer to this question. It has to be equal to 1 exactly, right? Because it's probability of being anywhere. Right, but let's look at the structure of psi. Right, so psi is e to the I kx. Right, so if I take the square of it, I have the integral from 0 to x1 of e to the I kx squared dx. Right? And if we integrate that, we get a value because e to the 0 is 1 and e to the I kx1 is an imaginary number, then we square it. You can see if I take x to be infinity, right? If I make the box bigger and bigger, what does it mean? Well, it means what I'm doing is I'm basically integrating around this circle. As the particle moves in position, it's actually traveling this circle in the complex plane. And so my integral is basically just an integral of the circle. And so if I let x go to infinity, all I'm doing is allowing that atom to travel around the circle over and over and over again. And so what it's going to do is just continue to accumulate phase. It's going to go around the circle. It's going to get 2 pi. It's going to go around. It's going to get another 2 pi, so on and so forth. Right. So every time I integrate, I'm adding an area of that circle. And so if I go to infinity, the integral goes to infinity. So this doesn't work. This will diverge as x1 goes to infinity. So this doesn't work. Right. So as the box gets bigger, this integral diverges, and that's not what we want, right? We want it to converge to a value. So this doesn't work. Okay, but there's something else we can do with complex numbers, right? Complex numbers have this conjugate structure to them. We can take a value that's complex, right, e to the ikx. But a reasonable solution to the problem is also e to the minus ikx. And really what we should think about is that when we square the function, instead of squaring the e to the ikx and doing it again, putting two e to the ikx's together to get e to the 2 ikx, what we're going to do instead is choose to multiply e to the ikx with its complex conjugate, e to the minus ikx. And so what then I have is e to the ikx going clockwise around the circle, accumulating phase in a clockwise fashion. And e to the minus ikx, which I'm multiplying it by, is going in the opposite direction. So any phase that e to the ikx generates, it's canceled out by e to the minus ikx. All right, so instead what I'm going to do is write the square. Let's go ahead and go to the next page. But what I'm going to do instead is integrate from negative infinity to infinity, right? That's an infinite box. Psi squared. But I'm going to write it instead as an integral from minus infinity to infinity of e to the minus ikx times e to the ikx, right? Which is psi times its complex conjugate. All right, and now it's much easier. This math is much easier, right? I can now, I've got. Oh. Can you guys give me 30 seconds? I got to take this phone. I apologize. It's the HVAC guys trying to pick my words. Everybody else is literally frozen right now.
Did you see Joe's back? Yeah. Joe, what am I myself into? Low key. Like low key, we need to slow them up for right now. That's what I'm saying. Dude, like that's what I'm saying. That he's yeah, so please don't year and a half, so like closer, but yeah, 2 years. It's been like a lot.
Oh, sorry about that.
Oh, that was quick.
They were like, is the back door unlocked? Yes, it's been unlocked. I'm just going to have them come in. All right, so this math is easy, right? We have a multiplication of two exponentials. We just add the exponents. E to the ikx minus e to the ikx, right? That's 0. So this is just the integral of 1. Infinity to infinity of 1 dx, which is just 1. All right? Perfect. So what does this mean? Well, this just means that if we think about our space, x, 0, put that in the middle of the room, right? And you ask, what's the probability of finding the electron or the atom anywhere in the box? It's just a straight line. Right? So psi squared is just a straight line. It's just equal to 1. Right? So what does that mean? That means we have a uniform probability, meaning that there's an equal probability of electron being, or the atom being anywhere. So the atom is completely delocalized, like a wave. It exists everywhere, just like we expect from a wave in space. Right? And the key for this is remember that x and p are incompatible measurements. What we have is a wave, e to ikx. It has a fixed momentum. It has a fixed momentum because it has fixed energy. How we solve this problem, we're looking for states of constant energy. And so what happens is that now the momentum is h bar k. It's a defined momentum, which means the position is completely undefined. Right? Remember, x and p are incompatible. So if we define one, the other one is undefined, and vice versa. So this is that. picture that this atom is not really localized anywhere in the box. It can be anywhere. Right? That's not very interesting, but it's an important result, and it kind of is a good sanity check for us because this is what we would expect. If it's an atom, it doesn't have any preference to be one place or another. Every space at point in space is exactly the same. There shouldn't be any bias. I think that's exactly what we observe. Now, one thing that we might want to try is to find some way to bias it so that we can localize it. And that's going to be our goal. In fact, that's the goal of chemistry, is to basically find a theory of localized particles and how do they function, because that's what an electron is, right? An electron in an atom is stuck to that atom. It's confined in a space. So we should think a little bit about what things look like when they're confined as well. Okay, before we think about confinement, say put an electron in a bond, we should think about a little bit about the properties of this system, and if there's anything we can learn about. And so the thing I want to look at in particular is this formula here. The momentum of this object is a number k times h bar. And we've got some formula for k up there. It has something to do with the energy. And so people noticed when quantum mechanics started to become a thing and people were appreciating this wave-like structure for these particles, they had to rationalize it because it didn't make any damn sense, and it's contradictory to other observations that classical physics does, right? So people are starting to think about the philosophy of these wave-like objects. And there's a particularly interesting Frenchman. He's not a scientist by trade. He's a really, really rich nobleman, kind of a fail son of a noble family in France. He kind of, if you've ever seen Arrested Development, he's a bit like Buster Bluth, meaning that he's not a super useful person, like he doesn't work that hard, but he's got tons of money, so he just spends his entire time studying at home. It's a man named Broglie. And Broglie comes up and starts thinking about this wave-like hypothesis. Okay, and what he does is he says, okay, well, we have this idea that momentum is this number h bar, which we haven't defined yet, but we will in just a minute, times this k, which is a number. And then he goes back and thinks about the equivalent k for light, which we call the wave vector. And in light, which of course is the canonical wave. So this is for our particle, right? For our wave, our light wave, you can write that k is equal to 2 pi divided by the wavelength of the light. Right? This k has to do, in some sense, about the spatial size of the wave. Right? Waves have a oscillate in space and in time. K tells you, in some sense, the extent of the wavelength, right? How big the wave is from peak to peak. Right? It's inversely proportional to it. And so he says, okay, let's combine these two things together, right? His hypothesis is that, well, if particles are waves, they have this momentum h bar k, and light waves have this structure to their wave vector. Let's put them together to make one equation that relates the two ideas together. And so what he puts together are these two. And he says that P is equal to 2 pi h bar over lambda. Okay, so what he says is that the momentum of an object is inversely proportional to its wavelength. And then, but it's proportional by this factor 2 pi h bar. All right, and you can actually take this law and then start to think about how lambda is related to the frequency of light. And the frequency of light, this is the frequency in hertz, is equal to c, the speed of light, divided by the wavelength. And you can also then, therefore, put these equations together and then relate momentum to energy. And you find that E, the energy of the particle, or of the wave, is 2 pi h bar times the frequency. Okay, so what this is now, what we've done is we've taken electromagnetism, the theory of waves, massless waves, photons don't have what mass, and the theory of the momentum of wave-like particles, and we've combined them together to get a relationship between wavelength and frequency of the wave and the energy and the momentum of the particle. So now we have two equations that tell us something about the wave and the particulate qualities of the light or of the system. It doesn't matter if it's light or it's, notice that there's nothing in here about mass. Right? We'll have to think a little bit about what the momentum of light might be, because it doesn't have a mass, so m times v is 0. But for massive particles, we can relate energy and frequency, wavelength and momentum. They're all interrelated to each other. Right? So this now necessitates, right now we have a conversion between particulate concepts and wave concepts, and they're proportional to this value h bar, this constant. Now it's time to talk about this number. As you can see, the h bar it's a number, it's a constant. It ties all the concepts together. It ties the particulate part and the wave part together. And the way that we relate them are basically the conversion factor between those two regimes is this function, this factor h. Right, so let's introduce this constant. We're going to see it all the time, right? As you can see, the energy is related to h always. So anytime we talk about energy, h is going to appear. Right? And so this constant, I'm going to just kind of put it in a box over here. H bar. Right. So we define, this is what's called Planck's constant, named after Max Planck. This is the official name for it, and it's an SI fundamental constant of the standard metric units. Okay, just like the speed of light is, and the Boltzmann constant, the gas constant, Avogadro's number. These are all numbers that are fixed in metric units. And Planck's constant is also fixed because it's just as essential as the speed of light and the gas constant and whatever else you can think of. Okay. And we define Planck's constant in two different ways. There's two different versions of it. As you can see, I've got this factor of 2 pi here in some of these equations. And so there's a function, there's a constant we call Planck's constant, which is 2 pi h bar. And then there's what's called the reduced Planck constant, which is just h bar. I'll write them down. They're just different by 2 pi. All right, so h bar is called the reduced Planck constant. Okay, let me give you the number of it really quickly. I'll give it to you exactly. All right, we often call this, I'll give you the name of it. So every time you hear h bar, we call that the little line through the h is the bar, so h bar. And it's equal to, let me get the exact value. I know it to like 4 digits. I don't know it to all the digits. I want to get them all for you. And my mouse is gone. There it is. Okay. 1.0545718 times 10 to the minus 34. It's a small number, joule times seconds. All right, we'll look at those units in a second. All right, why is it joule seconds? It's not joules per second, it's joules times seconds. Okay, we'll look at that in a second. And then there's another constant that we use, which is the same thing. It's called h, which is just 2 pi h bar. Okay, and we call this the Planck constant. It's the original. Right, and it's just the same thing but multiplied by 2 pi. Right, and this is 6.626070015 times 10 to the minus 34 joule seconds. And those are defined exactly. There's no errors on those constants. They're fixed. Okay, those are really, really small numbers. Let's think about the units a little bit. Right? So I can rewrite these equations, right? And more simply, I can write this as P is equal to H over lambda, and E is equal to H nu, the frequency, right? This equation we're going to look at for a little bit, and then we're not going to really use it that much because it's not super useful for chemistry, but I'll give you a nice example of where it's useful. This equation is perhaps the most important equation in all chemistry. E for Hb, nu. The reason why is this is spectroscopy. This is the key of spectroscopy, is that we can shine light a frequency nu, and we get energy from it. And this is how we excite molecules, right? We feed it in some light of some energy, some frequency. It pumps some energy into the atom and excites the atom, right? This is our interconversion between light frequency as a light wave and energy in terms of like a physical quantity energy, right? Very, very important. Right, so this is called Planck's law. All right, and I'm going to, if you remember anything in this class, take one thing home from you, it's this equation. It allows us to take light information, wave information, and convert it into information that's useful for chemistry of particles, joules. And now we can understand a little bit about the units. H is joule seconds. Nu is a frequency, which is, in some sense, how many periods the wave travels per second. So how many periods does it oscillate per second? So nu is, the units of nu is periods or 2 pi radians per second. Right? 2 pi radians is not a unit. So we say that nu has units of per second, which is hertz. And so when we multiply it by H, we get joules, right? Joule seconds times inverse seconds is just joules. So we get energy. Okay, so that's those units. What this says is that we can look at that energy, but it's a really, really small amount of energy. Okay, so here's an example. Imagine you have one photon of infrared radiation, right? Something that excites a molecule in your IR spectrum. It doesn't do it. I'm just going to do it roughly. The frequency of infrared radiation is around 10 to the 15 hertz. And so it oscillates 10 to the 15 times per second. So we could just plug in 10 to the 15 here. Right? We've got an infrared photon of 10 to the 15 hertz. And the amount of energy that it provides the molecule is 10 to the minus 15 times, or 10 to the 15 times 10 to the minus 34, which is like 10 to the minus 21 joules, right? So one photon only brings to the table 10 to the minus 21 joules. But if you have a mole of photons, right, you're starting to talk about joules of energy. And so the important thing is that each particle brings a very small amount of energy into it. But remember, in chemistry, we're dealing with Avogadro's number. And we can even multiply this number by Avogadro's number to get the joules per mole second. That's an interesting idea, right? And that kind of would be somewhere around 10 to the minus 9, right? So a mole, depending on the frequency of the light, a mole of photons brings somewhere around 10 to the minus 9 to 10 to the 3 joules per mole of photons, right? So when you have lots of photons, you can provide lots of energy. Likewise, light has a wavelength. So light can also provide a momentum. Right? So what that means is that if you collide something with a photon, it provides some energy to that object that's absorbing it. And because of conservation of momentum, it accelerates the object that it hits. Right? The photon colliding against a floating box, if you will, or floating panel, gives it a push, a kick. So I could shine light, like imagine I have in fact, this is an idea that people have. Imagine I have a sail, like a sail, and they even have these satellites that have these. They have these sails. And the idea is the sails pick up all the light and the particulate matter that come off the sun. And so when all the excited protons and hydrogen atoms and different things hit that sail, it pushes the sail along, right? As these little particles berate the sail. but light also provides that push as well, because light provides an incident momentum due to its wavelength. And so you can make these sails. The idea is that you can get your object to accelerate passively out of the atmosphere, not out of the atmosphere, but say out of the inner solar system, get it speed up by having these sails and just basically having it absorb all the light and the particles coming from the solar winds, and it will accelerate that thing all the way up to the speeds that a normal satellite does without using any energy. All the energy comes from the incident momentum of the light. And in fact, if you look at really, really interesting theory, there's 2 satellites in space right now that have exited our solar system, Voyager 1 and Voyager 2. They are now officially out of the solar system. There's actually the shock wave at the edge of the solar system that they passed through. They've shown that they passed through that shock wave. Now they're basically in between solar systems now. And what you can see is that, again, that the engines on those Voyager probes are long gone. They had plutonium-powered thrusters that accelerated them, and that plutonium is all depleted at this point, so they don't have any more thrusting. Okay, so they're just floating objects. But if you look at their acceleration curves, they're still speeding up. And the reason why is because they just happen to be close enough to the sun. They're actually past the point where the sun's solar winds are hitting it, but they're still receiving radiation from the sun, and the momentum from that radiation continues to accelerate them very slowly. So they're actually getting faster as they leave, even though they're formally not moving. They don't move on their own volition. Right? So photons can provide a momentum as well from this. Let's think about a chemistry application. What this says is that if we can think about the velocities of objects, say we have a gas. You guys remember last semester, those who were in Pekin 1, that if you have a gas at some temperature, it has some velocity, right? The particles are moving. So what if we have a series of atoms that are some temperature? We ask the question, we think about how fast they're moving in our gas. What's their wavelength? Do they have a wavelength? Is it relevant to even think about them as waves at a standard temperature? So I want to explore that briefly. So I want to apply de Broglie's hypothesis to a kind of a classic example of where it may apply in chemistry. What I want to look at is liquid helium. Okay, helium again is a monatomic gas. Monoatomic gas. Right? And we know that the mass of helium, we don't even have to be that precise for this calculation. We know it's about 4 AMU. It's about 4. Right? It's about 4. Okay. And we can go look at where helium liquefies. And the transition temperature, the liquid temperature, where it goes from gas to liquid, is, let me get it exactly, 4.15 Kelvin. Okay, so helium doesn't interact very strongly with itself. So there's very few interatomic interactions. So to get it to condense requires very, very low entropy. Otherwise, it just boils. So what I'm going to do is we're going to drop helium down, say to 4 Kelvin. And and we have it at 4 Kelvin. I want to ask, we say we have a mole of it. What is the wavelength of these helium atoms? Right. The idea is this. Imagine the liquid, let's just think of it kind of simply, like not as a liquid, but like a crystal of helium atoms. We have helium atoms on a grid, a 3-dimensional grid. I'm not going to draw a 3D. Just a couple, looks like a tic-tac-toe. And we got some helium atoms, different positions, right? Is it fair to consider them like this, where they're just spheres sitting on a lattice, right? Or should I think instead of this atom at the bottom, as something that's highly delocalized, a wave-like particle that's delocalized over the space, right? So is it particle or a wave at this temperature? And the idea is that if the average distance between two atoms is d, right? If lambda is much greater than d, it's wave-like, right? And if lambda is much less than d, then it's particle-like, right? The idea is that the wave properties of the atom are a much smaller scale than the distance between the atoms, so that we can distinguish each of the atoms very clearly. But if the wavelength is much greater than the distance, then this atom overlaps this atom overlaps that one overlaps that one. They're all kind of conflated together. And so it's not clear if you can really treat them as particles. Okay, so what we can do now let me get the right equations here. Right, but what we can show, I'm not gonna derive this, but what you can show is that you can say, well, the energy of the system, the average energy of a system at a given temperature is around 3/2 RT. That was one of those things we learned in PChem 1. The average energy is 3/2 RT. Right, and I can take the momentum equals h over lambda, okay? And I can calculate lambda from this expression. Using the moment, given I know the energy, I can calculate the momentum of my object. And what I get is that the lambda for this system is Planck's constant divided by the square root of 2 times the mass of the object times RT. All right, we have to be careful of units because we have moles in the bottom, right? So we're going to have to be careful of everything. So what I want to use here is actually the molar mass in the bottom. Molar mass. Okay, and so what are the units at the bottom? The units at the bottom are going to give me R times T gives me joules per mole. This gives me kilograms per mole. Yeah, that's right. And then once we divide by H, we're just going to have a length. We'll cancel that. Oh, I missed a pi. Sorry. I know I missed something there. I know I'm missing. So it's 2 pi molar mass RT. Okay, so all we have to do now is just calculate some things. Okay, let's first calculate RT. That's 8.314 joules per mole Kelvin times 4.15 Kelvin. Let's just make it, well, yeah, we'll just do that. It's fine. Let me pull up my calculator. That's 34.5 joules per mole. Okay. 2 pi MRT is going to be 2 pi, which is like 6 something. Molar mass, we'll just say is 4. Actually, we need to do it in kilograms. So that's 0.04 kilograms per mole times 34.5 joules per mole. Okay, and so that unit is 0.04. 34.5 times 0.04 times 2 times 3.14. Okay, so that's roughly 8.7. And the units are a little weird. They're kilogram joules per mole. Mole squared. Sorry, there's a mole squared there because we have moles times moles. Okay, and what we're going to have to do now is convert H into moles because we have moles in the denominator. We're going to have H needs to have moles as well. So all we need to do is multiply H by Avogadro's number. So I'll put Avogadro's number here. And HNA is 6.636 times 10 to the minus 34 joule seconds. And Na is 6.02 times 10 to the 23rd per mole. Okay, that's not a hard calculation to do. This is roughly 4 times 10 to the minus 10 joules per mole. Okay. And so now we can just finish up our math here. Right, so this means that lambda now is equal to 4 times 10 to the minus 10 joule seconds per mole. Sorry, this is joule seconds because H has a joule seconds in it per mole. Divided by the square root of 8.7 kilograms joules per mole squared. All right, and once you do that math, you'll realize that everything works out the way you want it to. (1.35 times 10 to the minus 10 meters). Okay, so that means that the wavelength of this helium atom, 4 Kelvin, is 1.35 angstroms. Remember that a bond between two hydrogen atoms, for instance, about an angstrom. So this helium atom is actually the extent of one period of its wave is over the length of a regular hydrogen-hydrogen bond. It's big. Consumes the atom. If you think about the atom, the radius of a hydrogen atom in its ground state is about half an angstrom. We'll see that actually. We'll calculate exactly in this class. About half an angstrom. So you should think about atoms as being kind of on the order, like the radius of a typical atom is on the order of about an angstrom. And what this is saying is that actually the wavelength of the atom is longer than that rate. Okay, so what that means is that at 4 Kelvin, the wavelength of the atom is bigger than the atom itself. Or rather, I should say that bigger than what we perceive it to be as a particle. Right? These are chemical length scales. So what happens, right? So at 4 Kelvin, let's go ahead. I'm just going to draw the lattice one more. I'm just going to draw it like just a tic-tac-toe lattice. We've got 4 atoms here in our lattice. If you go look at liquid helium and you go calculate exactly what the average distance between two helium atoms is. And liquid helium, it's about 4 angstroms, 3 or 4 angstroms. So this distance right here is about 3 angstroms. Okay. And the wavelength of the atom is 1.35 angstroms, right? So you can kind of think that this system has a wave that extends out like this. And then the other one, which is the one on the right, extends out and kind of overlaps it. Right? So there's actually some probability, right? There's some probability that both atoms are in the same place. Right? So what happens as I start to drop the temperature, right? Maybe I want to freeze it out into a solid, right? How deep do I need to go? How cold do I need to go to make this freeze? Well, what happens to the wavelength as a function of temperature? It gets longer, right? Because it's lambda is equal to 1 over temperature. So as the temperature drops, the wavelength increases. So as I bring the system lower and lower in temperature, let's just say that this is 4 Kelvin, and I drop it down to 1 Kelvin, right? My wavelength now is twice as long as it was before. And so now the atom on the left extends twice as far out as the other one. And the same is for the atom over here. Right? So you can see as the temperature goes down, thinking about helium as a a conglomeration of particles that are all floating around at some average distance themselves breaks down. Because in reality, there are large regions of space where both helium atoms can exist at the same time. They overlap space. So that what that means is that the atoms are never in some sense independent of each other. So at low T, right, the particle approximation breaks down. It just looks like a bunch of waves. Right? So cold helium is really just a bunch of waves. Overlapping waves. All right. So the question therefore is, does it ever become a solid? And the answer is no. Because what do you need to have a solid? You need to lock those atoms into place, and they need to be fixed in place. Take a crystal. Those atoms are fixed in the specific positions in the crystal lattice, just like I've drawn here, right? This is what we would want. But once I bring the temperature down low enough to where I think I'm going to be able to freeze it, now, in fact, the atoms are no longer really in lattice positions anywhere. They're distributed. And so the atoms are never stuck in place. They're constantly swapping with each other. This atom's going here, this one's going here, right? That's kind of what it looks like because the probability distributions overlap. So these atoms are constantly changing with each other. They're constantly exchanging through the fact that their probability distribution is delocalized. There isn't really a specific lattice point that they exist at. So these atoms are all delocalized. They don't form a lattice. Right? And the only conclusion is that there is no solid phase of helium. I don't know where to write that. I'll just write it here. Right? The idea is that once it gets cold enough below the liquid level, these atoms are moving, even though they're moving really, really slowly, we don't expect them to move around. Their wavelengths are large enough that, in fact, they're just interchanging with each other. Even though they have no motion, like they're not actually moving. They're 1 Kelvin. They're frozen stiff. But their wavelengths are so long that their probability extends far beyond lattice spacing. So helium never freezes to a solid. And I can show that to you if we look at well, I think I showed it to you on your final exam, but not everyone saw it. If we look at the helium phase diagram, it doesn't really, one of them is helium-3, helium-4, it doesn't really matter, but well, you can see if we're at 1 bar, just typical pressure, we start with a liquid, we cool. There's no solid phase that ever appears. Eventually we go into the superfluid phase, which I kind of mentioned on the final exam, not a solid phase. What this is, a superfluid is a phase where all the atoms they're so completely delocalized you can't tell them apart anymore. Instead, now you have a fluid that has a distributed probability density for all the atoms. All the atoms are in the same state. You can't tell them apart anymore. It's just the density of atoms. It's not a collection of atoms that have individual spots. It's just one big density that moves together. That's what we call a superfluid, where the whole thing is one big wave function. And you can see, and so you don't ever get a solid. The only way to get a solid is to really start to put pressure into the system to force the atoms closer together, reduce their ability to move, right? And then it'll start to freeze out. But in normal position, normal temperatures, or normal pressures, there is no solid phase. Okay. That's pretty cool. Right. Hydrogen. Now you may ask, well, what about hydrogen, H2? It's a good question, right? H2 is even smaller. It has a mass of 2. It should even have a bigger wavelength. But it's interesting, it turns out, because of the way hydrogen works, very, very subtle, hydrogen can't exchange quite as readily as the helium atom does. Very, very complex reasons. But hydrogen even it's also longer, right? It's got a bond. So the hydrogen molecule is like a little bigger than a helium atom. You have 2 atoms at distance. So you have that combined with special properties that hydrogen has. Hydrogen molecules, they can freeze into a solid. You can make what's called metallic hydrogen, which is hydrogen frozen in a crystal. But you can't do it with helium. Very interesting. the fact that the molecule can rotate, the hydrogen atom, the molecule can rotate as well. That also helps it freeze. Helium atoms, you can't rotate them, they're just balls. So lots of really interesting properties. Okay, so there's my free particle application in chemistry. I can already predict helium's never going to have a solid phase because the wavelengths delocalize at low temperature. And you can't think of whole cold helium as a collection of atoms. You have to think of it as a collection of waves that are all overlapping each other. Okay. What I want to move to now is to put our particle and atom. What we're going to do is move to electrons instead, because we're going to do chemistry. We're going to think about electrons moving around in confined spaces between atoms. We're going to study that very deeply. The interactions that electrons have with each other in bonds. And so what we're going to have to do now is take our theory of a particle that's free to move wherever it wants and now confine it into a space, right? We have a box. You can think of it as two atoms, two different edges of the box, right? It can exist between the two atoms in a bond, but not outside of that bond. Okay, so let's start looking at that confinement problem. And I can find my next one. Ah, here we go. Fantastic. Oh. All right, so we're going to talk about it as a confined particle. We have a better name for it that's kind of like what they call it in the textbooks. It's this model called the particle in a box. Now, you guys probably know from previous alum that I love my particle in a box theory. I'm actually going to emphasize it less with you guys than I have in the past. Because what we're going to see is that the particle in a box theory just falls out of the map that we've already done. It used to be that I kind of built everything with particle in the box, but what we've done is kind of started even more fundamental and everything's kind of fallen out. And we're going to see that the particle in the box model just falls out of our theory of a free particle, but we put it in space, fixed space. All right, so let's design our problem. All right, so our particle that we're going to choose is an electron. All right, electron has a mass, m sub e, and it's a very small particle. It's about 1,000th of a proton. A proton weighs roughly 1 AMU, and a mass of electron weighs slightly less than 1,000th of it, 9.109, 3837015. It's an amazingly accurately measured number, times 10 to the minus 31 kilograms. All right, tiny little thing. Right? It's about 1,000th of an AMU. Of course, electrons have other properties. It has charge, which we're not going to really think about right now. We'll come back to the idea of charge. It has a -1 charge. Right. There's another property that we'll talk about later. You guys have already seen this. It's called spin. Spin can be plus or minus 1/2. This is the same thing as saying up and down deflecting. So there are two possible deflecting states of an electron. All right, we'll study that math in much more detail. So that's our electron. Does anyone happen to know the size of the electron, the radius of the electron? Any guesses? We have atoms have a size. We'll see the hydrogen atom's radius is about 1/2 an angstrom. Does anyone know what the radius of the electron is? No one? It's 0. It doesn't have a size. It's a point. People have studied, it's actually one of the most well-constrained properties in the world. is the point-like behavior of an electron. This is the most accurately studied. Let me just put it this way. No one has failed harder at measuring something than the physicists that try to have measured the radius of the electron. They've made incredible strides over the last 30 years to make more and more precise measuring tools to measure the electron's radius. And every single one of them has failed. It's interesting. Okay. So as far as we know, it has 0 size. Already you should freak out a little bit. It makes sense that a photon, light particle, has no, and therefore has no size. It makes a lot of sense that something has no mass and has no size. It wouldn't make sense if it had mass. It wouldn't make sense if it had no mass and had size, right? It doesn't make a lot of sense. But here we've got something that also doesn't make sense. A particle that has a mass, you can measure it. You can measure the mass very, very accurately. It has no size or shape, right? Which drives home the point of the wave-like characteristics of this system. That particles are not really particles, really, they're waves. And the sense is that this particle an electron is in some sense completely delocalized. It has no shape. It is constantly delocalized over space. Okay, so it doesn't have size. Very clever. Right, and what I want to do now is instead of thinking about my electron in the universe just kind of floating freely, I'm going to put it in a box. So I'm going to define the box. We can define it in different ways, but I'm going to define the box of length L. Right? So we have this region that the electron can exist in between 0 and L. And the box has infinite walls. All right, so on each side of the wall, each side of this, there is a wall that is impenetrable. All right, but the electron is freely allowed to exist anywhere inside the box. Okay, infinite walls. All right, this goes to infinity. So it's a completely trapped, confined particle in box length L. All right, so how do we represent in our calculations a system that is defined in this box? And how do we, in some sense, encode the box into our calculation? How would we change our calculation of the free particle to include the box? Well, you can think about when we integrate over the system, when we integrate over the wave function squared, we only need to integrate from 0 to L. So that's already, we have finite space instead of infinite space. But we have to think about where the wave function, what values the wave function has to have. Because if this box is infinite, the wave function, excuse me, the wave function outside of the box has to be 0. Okay, so e to the ikx doesn't work anymore. The reason why it doesn't work anymore because e to the ikx is non-zero at many points outside of this region. So we need a wave function that basically goes to 0 at the edges. Right? We don't want to have any probability outside. The wave function 0 out here and it's 0 out here, and then it's got some values on the inside. All right, so we'll have to think about what does how do we meet? We'll need to massage the function that we choose to represent the system so that it satisfies those constraints, the boundaries. So let's define those boundaries. The way that I'm going to think about this problem is to think about how much energy the system has to put in to exist in one of the two spaces. There's inside the box and outside. So the way we're going to look at it is that there's no penalty, energetic penalty for the electron to be in the box. It's free to be in the box, no problem. Box doesn't care. From the point of view of the electron, every point between 0 and L just looks like free space, right? It looks like this room, right? But then we have walls on the end. And the idea is that we're going to give it infinite energy penalty to escape the walls. Okay, so it costs infinite energy to escape. So what we're going to do is define a potential energy instead. So we'll define this as a potential energy. This box is a potential energy function. So box as potential energy function. Right, and the potential energy we call V of x. Right, and it's got two values. It's not really a function. It's just either 0 or infinite. So we could say that the potential function is 0 between 0x and L and infinite elsewhere. Okay. So we're just going to bias the electron stay within the box. Okay, so what we can do now is then write the total energy of this problem. So the total energy, which we call H for the Hamiltonian, I'll write that in a second, is equal to the kinetic energy plus the potential energy. Okay. So then we have to write an operator for this wave function. Right? We want to solve the equation. So we promote this to an operator H. This is what's called the Hamiltonian. And that's going to be equal to the kinetic energy operator plus the potential energy. All right, so we're just going to take our classical physics ideas and promote them to operators and hope that everything works the way we want it to. All right, and we'll have to solve if it doesn't. Right, but we already know the kinetic energy operator because inside the box, it's just an electron or a particle that's moving around. It's exactly the same equation that we had before for the free particle. It's minus h bar squared over 2 times the mass of the electron times the second derivative, right? Plus the potential, all right? And the potential depends on where we are in the box. Okay, so I don't really need to write anything here. It's a potential of x, but it only takes 2 values. So in the box, h is just equal to t, and then out of box, h is just equal to infinity. Okay, so we don't have to think about outside the box, but it does have a conclusion. There's no probability we're ever going to find the particle outside the box because it's infinite energy. So what this means is that the wave function outside the box, call it outside x, is just 0. Okay, all right, we already solved half the problem. So it's 0 on the outside, but obviously it might not be 0 on the inside, right? Because inside the box, it's just a normal free particle. All right, so we already know what that looks like. It's e to the I kx, but remember, e to the I kx doesn't necessarily have the right properties. What are the properties for that wave function? Okay, so the properties that we need, in some sense, is that the wave function at the endpoints, right there and there, right? There's no probability an electron can be found in those regions, right? Once it hits the box, it goes to 0, or the edge of the box. So I know that the wave function at this points from the inside wave function at these points is 0. Okay, so whatever wave we have, it has to terminate at these endpoints. It has to go to 0. So we know that that means that the wave function kind of either has to look something like this, or maybe it comes down like this, right? Maybe it comes in like this, or it comes in like this. It can be positive or negative, right? But we know it has to come in that way, right? It has to go to 0 at the points, and then we know it's 0 everywhere else. So I can kind of just draw it like this, right? So what we have to do now is find a wave that has this property at the boundaries, right? A wave that ends at the boundaries. Okay. Well, waves have a really nice property, right? They have periods. And we know that every half period, the wave goes to 0, right? Because it goes, say, like a sine wave, it starts at 0, and at pi over 2, it's 0 again. So we can just start to think about what those waves might look like. Right? I'm just going to kind of just roughly draw it. Right? There's lots of different waves that work. Right? Here's a good wave. Right? Maybe this wave works. Right? That's half the period. Right? So that means that for this one, the wavelength, right? This is half a period. So the wavelength is 2 times the length. Right? That works. That might work. We might have a wave that completes a whole period. I'll draw it in purple. Right? Where the wavelength now is the length of the box. Right? We could have 3 periods or 3 half periods. That would look something like this. Kind of a rough picture, but that doesn't work because it has to go to 0. Sorry. But as you can see, that one doesn't work because it has to go to 0 at the end, right? So the only other one, right? So we have to start thinking, well, what are the ones that go to 0? It has to be maybe something like this. That works, right? This has a wavelength of 2L/3. Is that right? No, wait, hold on a second. No, that's sorry, that's L/2. Right? And so on and so forth. Right? So there's lots of different choices, but here's the interesting thing, right? The appropriate wavelengths are half wavelength. The wavelengths or half the wavelength has to be the length of the box, right? The wavelength has to be an integer multiple of half the length of the box. All right, so what that means is that wavelength has to be equal to some number n times L/2. So the only ones that work. So now I can't put any old wave into that box, any value of k, any frequency or any wavelength. I can only pick specific wavelengths that satisfy the boundaries of my box. Right? Where n is some number. Right? N is an integer. Right? So n can be 1, 2, 3, and so on and so forth. All right, but it can't be 1.5, it can't be 2. I tried to draw the 1.5 one. That starts here and then it ends at positive up here. That doesn't work. Like the wave function has to be 0 at the edges. That means that the wavelength has to be an integer multiple of the half of the length of the box. It's the only other way to fit the wave into here properly. All right, so that means that only, right, if we have a wave function who has a wavelength proportional to k, 2 pi over lambda, then that means only certain k's are allowed. Other k's are not allowed. Okay, so what that means is now what we can do is go back to what I think it was Connor's guess, is that we can use sines and cosines again. We have a finite space, they integrate to a finite number. We don't have to use complex numbers anymore. We can just apply a sine or a cosine. Right? I've just drawn sines and cosines. There's nothing particularly special. And they satisfy all the properties we want. They have a finite integration. They end at the ranges that we want. They oscillate exactly the way we want them to. Should be fine. So what we can say now is that the proper solutions of this problem of our particle in a box, we'll call this, I lovingly call this pain in the butt or PITB. The proper solutions are going to be superpositions of sines and cosines. All right, so I'm just going to write it generally. All right, we'll have to resolve the equations here, the numbers. Right, but we can already figure out, so k is the frequency, the angular frequency. We can convert that into wavelength and then think about how k relates to the length of the box, right, our conditions. Right, so we can already start to do that now. Right, so we have that, well, the equation that we had before. is that lambda is equal to n times L over 2. All right, so once you convert that to frequency, what you find here is that K has to satisfy this property, that K times L is equal to n pi. Okay, where n is an integer. How much time do I have? Okay, just a minute. But what did we also say about K? We have an equation for K for the free particle. We have the, right, it's related to the energy of the particle. Right, so I can also write from my free particle solution because this particle is still a free particle, it's just in a confined space, that K is equal to the square root of 2me over h bar squared. This is all square rooted. Okay, so I can relate these two things together. I can say that n pi over L is equal to the square root of 2me divided by h bar. Voila, I can solve now for the energy. I haven't done any math besides just a little trig and then related it back to my free particle. I can solve for the energy of this system. And so what you find is that the energy is h squared, I'm just getting rid of the pi's, n squared over 8ml squared. And notice that now this doesn't take any particular value. It only takes values proportional to where n is an integer. Okay, and so now what we have, right, if we looked at the free particle, if we look at it as a function, so we have a free particle here and then our particle in a box, and we looked at the different energy levels of the system, the allowed energies, we saw that the free particle can take any energy at once. So if I draw little lines here for each of the energy levels, there's an infinity of them, right? It's continuous. Right, continuous. Right, because energy here is h bar squared k squared over 2m, right? Where k can be any number, right? We can give a particle any energy we want. But if we want to keep it in a box and keep it constrained in a box, it can only have specific energies proportional to n squared. Right? So that means that there's a zero energy, which means no particle. There's one for n equals 1. There's one for n equals 2. There's one for n equals 3, and so on and so forth, and nothing in between. Right? So we now have, by constraining it, we have a discrete energy spectrum, right, that have gaps in energies that don't exist. No wave can ever exist with energies in between these 2 points. Right? These are energy levels. You guys remember orbitals from hydrogen, 1s, 2s, 2p? Those are energy levels of hydrogen. Right? These are energy levels of our electrons stuck in a one-dimensional box. And by adding a box, we make discrete levels by confining the wave to be in a certain space. Okay? So we'll explore this discrete energy levels more carefully next class. I'm going to do a little chemistry with it. Have a good one, guys.